Hello, my name is Noson Yanofsky. This morning we're going to do, this class is called Theoretical Computer Science. We're doing Sipser's book. We're up to chapter 3. Today we're going to finish up section 3.1, 3.2, and 3.3. This is all about Turing machines and variations of Turing machines and what they have to do with with regular computers. Okay, so last time we talked about Turing machines. We spent a lot of time dealing with Turing machines and we saw that to describe a Turing machine in all its details is a tremendous amount of work, and you have to describe every single rule, and there's a lot of rules to do even the simplest things. Okay, great. So what we want to do today is simplify things a little, and what do I mean by that? We're going to have like what Sipser calls a higher level description of an algorithm. Okay, a higher level description. So let me just say, till now we described exactly what the Turing machine has to do at every single point, which is very nice. But we also have to have another way of describing it. We can't do this. What we need is some way of just saying, look, I want the Turing machine to do this, and I don't want to worry about all the details. I want the Turing machine to do that. I don't want to take care of every single detail. We do this all the time when we deal with pseudocode. We sometimes say sort. Okay, how should you sort? I don't care. Okay, same thing here. We're going to have a higher level description. I just want to say this mimics what was done in the real world, in the history of computers. Okay, we started off with computers. You had actual circuits, and you had to tell the circuit what circuits to do. And then it got a little bit more that was too much. So what we did was we made a language, machine language, and we kind of told the computer what to do in machine language. But then we got, as time goes on, that gets, it's painful. So we invented assembly language, which was like a closer to English language than that. And then we invented higher level language like Fortran and COBOL and C and C++, etc., etc. Okay, and if you just think about a computer regularly, with the invention of a mouse and the invention of different things, we're trying to get the computer to be closer and closer to human language. Okay, so when we talk to Siri or we talk to whatever those stupid boxes are that connected to Amazon.com so they can sell you more things, it's almost human language. We want our computers to be closer to human language. It's easier than us going down to their level. And what we saw in the last class was it's very hard to go down to their level. So we have to go up to a higher level. Okay, so let me do a problem from the book. The problem is section 3 is numbered. Okay, so this is called a higher level description. Okay, it's on top of a formal description. And by the way, for the test, you have to be able to do both. Okay. Okay, so 3.8b. Okay, so what we want to do is write a Turing machine that decides the following language. W such that W contains exactly twice as many zeros as ones. It contains exactly twice as many zeros as ones. Okay? So what that means is for every zero that you see, for every one that you see, you should see twice as many zeros. Okay, so let's just go through a typical word. So twice as many zeros. question is this word in it. Now, as human beings, let's see how a human being would do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 of those. I can tell you now, this word is not accepted. Okay? Let's change it to 0. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. There are 5 ones and 10 zeros. Okay, so what did we do as a human being? We counted, okay, and we know what n is and 2n, and so we did that. Now, but I'd like to do it as a Turing machine would do it, okay? And again, this is a higher level description. We're not going to go through every single rule. This is a higher level description. I just want to say one thing. You don't need a Turing machine for this. This could have been done by a pushdown automaton. We had such languages, okay, where you have twice as many of one letters as the other letter. But I'd like to do it more as the way a Turing machine will do it. Okay, so this is an algorithm. We can write such things in algorithms class, but let's do it here. You ready? From the left of the input, strike out the first 0 you find. From the left of the input, strike out the first 0 you find. Okay? If you only find x's, then accept. Period. If you only find ones, then reject. Okay? So here's accept, here's reject. Great. 2. Okay? We struck out 1 0. Okay? Step 2. Strike out another 0. Because what we're going to want to do is we're going to strike out 2 zeros for every 1 1 that we find. Period. If you only find x's, let's say you don't have another 0. You only find x's or ones, then reject. If you don't find zeros, but you only find x's and ones, reject, because you didn't find 2 zeros for every 1 that you find. 3. From the left of your input, strike out the first 1 you find. Okay. Again, we're going to go through this very carefully, but I just want to say each one of these things can be changed into rules, Turing machine rules that you can write out exactly, but we're not. We're doing a higher level description. In other words, just like, computers really don't understand what Java programming is, but there's a compiler that changes it into assembler, which changes it into machine language that does understand it. So too, you can change all this into Turing machine things. Okay, but we're not gonna do this. Okay, if I strike out the first one, you find. If you okay, so you strike out the first one, you find. Period. If what happens if you don't find ones, but if you only find x's or zeros, reject. Okay. Step 4. Go to step 1. Okay, that's it. Okay, so the best way to do this is as follows. By the way, the word accept is only found here in the entire thing. All the other ones tell you how to reject it. Okay, great. So the best way to do this is to start here and go through an example. I'm going to find the from the left, so you start over here, from the left, strike out the first 0 you find. Strike it out. Okay, if you only find x's, no, I striked it out. If you only find 1s, no, I striked it out. Next, strike out another 0. I don't have to go back because this is the first 0 I found, so the next one will be the next 0 I found. Very good. From the left of your input, I'll explain to you why you need that, strike out the first 1. Good. Okay, go to step 1. Okay, so we're going to go, it says from the left of your input, strike out a 0, strike out another 0. From the left of your input, strike out a 1. Strike out a 0, strike out a 0, strike out a 1. Strike out a 0, strike out a 0, strike out a 1. Gotta go back. Strike out a 0, strike out a 0. Gotta go back. From the left of your input, strike out a 1. Okay, we're up to there. Now go back to step 1. Okay, from the left of your input, strike out the first 0. If you only find x's, I only find x's, accept. So it's accepted. Okay. However, okay, so this word is accepted. Stop. Don't destroy your notes. Let's just go through it. Let's say there was another 0 here. So look what we do. Strike out the first 0. I cross it out. Great. Strike out another 0. There is no other 0. If you only find x's or 1s, reject. I reject. Okay? Okay, so that's a nice higher level description of what a Turing machine is. And obviously, we like those things. So, so we're not going to do it. Okay, I just want to say, this was a homework problem, 3.8b. So this is the answer to the homework problem. I did a little harder one, but let me just say 3.8a is W contains an equal number of 0s and 1s. So that's a little bit easier. You don't just need this striking out the second thing. And C, I'm just giving you the answers to the homework. C was you'll read the question yourself. You swap all the rejects for accept. Swap all the rejects for the accepts for rejects. So that's the end of doing the homework problems. Okay. Okay. So that's a lot of examples of Turing machines. You're going to see. You're going to have to do them. Again, you're responsible for both formal, exact definitions and higher level descriptions. Okay, and the book does a few also. But I'd like to get back and talk more about Turing machines and what they're all about. Okay, so this is a nice example, but we're going to get back to Turing machines. So what we have to do now is describe what a computation is. Okay, what is a computation? What does it mean to get a Turing machine to compute something? Okay, so first thing we need is a definition. Definition. A configuration is the total information of where a Turing machine is up to. Okay? This has some other names. Okay? So a core dump. I don't think the book uses this, but we use this. Sometimes when you're writing a program in an old computer, you can do what's called a core dump. And what it does is it tells you every variable, what the variables are equal to, what's in the memory, where you're up to in reading the program, what line number of the program you're up to, gives you every single piece of information. Another thing this is called, I don't know if it's one word or two, is a snapshot. Snapshot. A snapshot is, again, it's the same thing as all this. It just gives you every single thing. Where is the computer up to right now? Okay? Now, these things, these three different names, but they're all the same thing. We're going to call it a configuration. They contain three parts. In other words, where the computer's up to for a Turing machine contains three parts. One, what's on the tape. Okay, what's on the tape? I don't want to use it as a question mark. It's telling you, period, what's on the tape. Okay, so remember, what's on the tape is both the input, the work, the output. All this is just that it's your memory. Okay, so everything's in the tape. Okay. 2. Where is the eye of the Turing machine pointing? Okay. In other words, your Turing machine is up to something. It's looking here, it's looking there, it's looking here, it's looking there along the tape. So I'd like to know, where is it pointing to? Where exactly is it pointing to? And 3, what state is the TM in? At any single point, it's in one state. Okay? And again, this was Turing's idea of what a computer is. A computer, sometimes it's in this state, sometimes it's in that state, sometimes different things. Okay. Okay? So this is what a configuration is. Let me give you an example. You might have on your tape 0, 1, X, A, B, Y, 3, Z, 2, 5. And you might have that he's pointing to that Y. And you might have that the state is in Q63. Okay? Okay, so that's a configuration. We write a configuration. We can draw a configuration like this. It tells you all three things. What's on the tape. Let's say the rest is all blanks. Okay. Where it's pointing to right here. And what state it's in, like that. We can write it like this, or we're going to write it like this. Okay. 0, 1, X, A, B. Okay. And now I want to say it's pointing right over there. So right next to where it's pointing to, right to the left of where it's pointing to, I want to put the state, Q63. And then I want to say, okay, Y, 3, Z, 2, 5, period. Okay? So look what I'm doing here. I'm saying what's on the tape. I'm saying where it's pointing to. It's pointing to the left. The pointer is to the left of where it's pointing to. Okay? And finally, I'm telling you what state. So this is what's configuration. Great. Okay? Okay, next. So this is what a configuration is. Again, we're aiming for the definition of computation, and I'll give you a hint already. A computation is a series of snapshots, like a movie made out of snapshots. So one snapshot after another, one configuration after another. Great. So now I need something else. Now that I know what a configuration is, I want to know, how do configurations change? because that's what computers do. They change configurations. They go from one state to another state. They go from something on the tape to another thing on the tape. Okay, so let's write this as an English sentence. How do configurations change? Okay, and it goes as follows. Let U, capital U, comma V, no, capital U, comma V. They are a member of the tape. They are both words of the tape alphabet. Okay? A, B, and C are a member of the tape. Remember, we had the input alphabet was for sigma, and this is a gamma. This is the tape alphabet. Tell me, what can be on the tape? Okay? Okay, great. Now we have two things. Again, we're describing how configurations change. So I want to show you how one configuration becomes another configuration. So we have the following thing. U, A, Q, I, B, V yields, that means changes into, okay, it becomes something else. It becomes U, Q, J, A, C, V. This is like a little, we focus in on one aspect and see what that changes. So you have a bunch of words here. You have a bunch of words here. In the middle you have a letter on the left, QI, and what's it pointing to? It's pointing to the B. Okay, let me just show you. This configuration will yield this configuration if, here's a Turing machine thing, transition function of QI, comma B. If I'm in state QI and I'm looking at B, that's going to equal to QJ, change the B into a C, and move to the left. Okay. That's exactly what just happened. I'm in state QI, I see a B, I want to change the B into a C, and then I want to move to the left. That's this way. So I was looking at the B, I changed it into a C, but now the I moved that way. Okay? Now this is one possibility. There's another possibility. Okay? And the other possibility is the same thing. We start here. U, A, Q, I, B, V yields U, A, C, Q, J, V. Okay, same thing. QI is looking at B. You're in state QI, you're looking at the letter B. So, if QI, you're looking at the letter B, if that's equal to QJ, change the B to a C, okay, change it to a C, and then, after you change the B to a C, I want you to go to the right. And that's exactly what just happened. You're in QI, you see the B, change the B to a C, and then move your I to the right, this way. The only difference between these two rules is here you're moving to the left, here you're moving to the right. So what we just did was we summarized all of computation. We went to the little bit, the little atom of computation. This is the little atom of computation. This is the little change that you make. Okay, you can't get smaller than this. Okay, if you're looking at something, you can change. You can move to the right. You can move to the left. You can move to the left. You can move to the right. Okay, and here this configuration will become this configuration if you're moving to the left. This configuration will become this configuration configuration if you're moving to the right. Okay? Okay, great. Let's talk more about other configurations. A start configuration in other words, your programs always start with a beginning, is this. Q0, that's your starting state. I think I might have called it QS in the definition. Q0, W. That's your input. So this is the way the Turing machine always starts. It's pointing this way, and here's where your input goes. And he's in state Q0. So that's your starting configuration. Okay? Then we have accepting configuration. What's an accepting configuration? Something like this. You have U, which is a bunch of symbols, Q accept, and V, a bunch of other symbols. In other words, I don't care what the state is. I'm sorry, I don't care what's on the tape. I only care you're in state Q accept. Okay? Rejecting configuration is U, Q reject. It's one of the states, V. Okay. Both of these are called halting configurations. I'm finished with this. Okay, great. Now we come to exactly what we wanted to do every day since the beginning of the semester. I told you, theoretical computer science deals with the following question. What is a computation? What can computers do? What can computers not do? Okay. Well, we have to decide what is a computation. So we're going to do this. Now, when we talked about finite automatons, I gave you an exact definition of what a computation is for that baby computer. Then we talked about non-deterministic finite automatons. I gave you an exact definition on one of the. Okay. Now what we're going to do is I'm going to give you an exact definition of what it means for a Turing machine to be a computation, to do a computation. Definition. A Turing machine M accepts input W member of sigma star if, hold on, now for a finite automaton I said what does it mean for a finite automaton M to accept a word? Okay, and we said what? We said there's a sequence of states. Okay, now here we have to be a little bit more sophisticated. We don't need a sequence of states because there's a lot of other things going on. Not just changing states, but a sequence if there is a sequence, just like before, but not of states, of configurations. C1, C2, C3, CK, such that 1, C1 is a, hold on, let's just remember what it was for finite automatons. We wanted the R0, the first state, should be a starting state. Well, guess what we want here? We want C1 is a starting configuration. Q0W. Okay, 2. I'm gonna do 2, but in a second, let's just do 3. 3 CK, that's the last one. Well, what did we have for finite automatons? It should land in an accepting state. CK is an accepting configuration. Okay, finally, let's do the middle one. What did we have for finite automatons? We wanted the transition function should take it from one state to the next state. Okay, now we don't have one state to the next state, but we have CI yields. That means gives, and 2 minutes ago I erased what it means for one configuration to yield another configuration. CI plus 1. Okay, so that's an exact definition of what a computation of a Turing machine does. What does a Turing machine do? It has a sequence of computations, starts from one, from each one yields the next one, those little local moves that we talked about, those atomic moves, okay, and finally it ends in an accepting state. Okay, so it's a generalization of what we saw for finite automatons. Okay, great. Now that we have a computation, we can talk about what words are accepted, what words are rejected, and things like that. So let's go through that. Okay, so we're building on to, we had to talk about configurations, we talked about special types of configurations, now we talk about sequences of configurations, and again, the image is as follows. A computation is a movie of configurations. Sequence, you start at one point, you finish at the end. Okay, then think of every one of your programs as a movie of little steps. Okay. You ready? We just had the definition of what it means for a word, a single word, to be accepted by a Turing machine. Now we say as follows. Let M be a Turing machine. We could talk about L of M, the language of M. Okay, this is equal to, let's write it up, the language of M, okay, which is equal to those words such that M accepts words, the W. Okay? So this is exactly what we saw before about finite automatons. You want to talk about what words are accepted by them. Okay. Now, here's where the shocking thing comes up. Okay? Because for finite automatons, for pushdown automatons, what happened? We start reading the word, we go through the sequence, sometimes we change states as we do, okay, that's for finite automatons. For pushdown automatons, we change states, but we also push things on the stack, pop things off the stack, etc., etc. For Turing machines, what could happen? We start reading, but you know what? Then we can go backwards, then we can go forwards, then we can change this, then we can change that. Then we can change this. Something new can happen for Turing machines which couldn't happen for finite automatons and pushdown automatons. For finite automatons and pushdown automatons, we start reading the words, we're eventually going to get to the end of the word, no matter what. But for Turing machines, one of three things can happen. One, we can accept. That's great. Two, we can reject. That's great. We saw these two things in the previous two machines also. But now, three, something new can happen. What's the new thing can happen? An infinite loop. And this is where all the interesting things go on. A computer can accept a word, it can reject a word, but it could also just keep on going back and forth and changing things and updating things, changing things, etc., until it gets, not until, so that it's in an infinite loop, okay? And it's not going to stop, okay? So now we have two important definitions that take this into account, this new thing, because beforehand, every word was either accepted or rejected. For finite automatons, for pushdown automatons, every word was either accepted or rejected. But now something new is happening. What's the new thing that's going to happen? We could have something else. Okay, so let's work with that. Okay, I need more room. Definition. A language is hold on, I just want to motivate this thing. Okay. Last time, finite automatons and pushdown automatons, we decided what does it mean for a language to be regular. Well, a language is regular if there exists a finite automaton that recognizes it. Okay? What does it mean for a context-free language to be context-free? If there's a pushdown automaton that decides it, that tells when it's in and when it's not. Okay, now we're coming to a Turing machine. Great. So we ask the following question. What does it mean for a language to be recognized by a Turing machine? Okay, so, but now we have to be a little bit more careful, because we have to worry, will the Turing machine sometimes go into an infinite loop? So we actually need two definitions, okay? And we're going to go through exactly the two definitions in a second, okay? A language is Turing recognizable. If, this is what we're defining, Turing recognizable. If some Turing machine M recognizes it. Okay? What I mean by that is, so a language L is equal to the language of M. Okay? Okay? We also call this, such a language, call it RE. Okay? RE stands for recursively enumerable. Okay? Now, why it's called that is an old story, and it goes back into history. I don't want to talk about it, but it's called that. But let's just see, okay? Let's just see untangle what this means. It means if the word is in the language, then M accepts. So we're talking about a language. We want to know, when is a language Turing recognizable? Well, if the word is in the language, then M accepts W. Say yes. It says yes. Okay? When the word is not in the language, then M rejects W, or M goes into an infinite loop. Okay? This is so important that I have to use another color and underline it. Or M goes into an infinite loop. So M accepts W if it's in there. If it's not in there and rejects it, that would be great, but sometimes it doesn't reject it, it just goes into an infinite loop, and you can't tell if it rejects it or doesn't reject it. Because you can't tell if you're in an infinite loop. It might stop in 2 minutes. We'll see this in a second. Next, so this is a definition. I defined what it means to be Turing recognizable. Recognize it. I recognize it when I see it. Okay? We need another definition, which is very similar but different definition. A language L is Turing decidable. Turing decidable. Okay? This is also called recursive. This is called RE. But when you look in other books, you'll see the word recursive. Okay? So recursive RE. Okay? If there is a Turing machine M, I just wrote it as follows, that gives a yes, no answer. For every word. Okay, let me explain to you what that means. Okay, that means if the word is in the language, then M accepts W. If the word is not in the language, then M rejects W. Okay? Here we had a third possibility. Here we don't have a third possibility. Either it's accepted or it's rejected. One of the other. Okay? And the computer has to give that answer. Okay? So we can think of this as a yes, no answer. Okay? That's Turing decidable. Decide, make a decision, yes or no. As opposed to that, here we can think of this as a yes, no, maybe. A yes, no, maybe answer. In other words, I'm not going to give you a full decision. Sometimes I'll say yes, sometimes I'll say no, sometimes I'm not going to say anything. Okay? Now, a language, and we're going to see examples of this, these are slightly simpler than these. In other words, if I can give a yes-no answer, then computers are very good. Then the language is simple. I can give a yes-no answer. More complicated languages, sometimes the computer can give a yes-no answer, but sometimes computers cannot give a yes-no answer. They're just looking for an answer. Okay, and we'll see examples of these two things, a lot of examples in 2 minutes. Okay, let's go through it. Okay, I want to do the simpler example in a second, but I want to do the simpler example first. Consider the following language. Okay, now we're talking about languages, and we want to know when they're Turing decidable, when they're Turing recognizable. Okay, so here's a language. A to the I, B to the J, C to the I times J. Okay, I think the book actually wrote this language. Okay, this language, let's just think about it. Forget about a Turing machine. Let's think about a regular machine. How would you do this with a regular machine? I give you an input with a bunch of A's followed by could be a bunch of A's followed by, I give you an input with letters A, B, and C. I want to know if it's of this form. Well, first thing you could do is go through the word, make sure it's all the A's, followed by all the B's, followed by all the C's. Nothing else, nothing out of order. The next thing you do is, while you're counting, count how many A's there are, count how many B's there are, calculate what the number of A's times the number of B's are, see how many C's there are, make sure it's the same thing. You did it. Now, let's say a word's not in this language. Well, the computer will say reject. Okay? The computer's basically going to read from the beginning to the end and do this. Okay? The Turing machine can easily do this. Okay? It can give a yes/no answer. So this language is Turing decidable. Give a yes/no answer. Now, here's another way of thinking about this. When calculating this, a computer will never go into an infinite loop. When deciding whether or not a word's in there or not, it won't go into an infinite loop. Okay? So this is a first example. It's Turing decidable. Okay? Now let's do another one. Polynomials. Okay, I don't want to go through what a polynomial is, I assume you know, such that, okay, let's write this in one variable, okay, such that P of n, I'm sorry, there exists an n such that P of n equals 0. Okay? Okay, so polynomials with just x, let's say, okay? And what, now I don't want all polynomials, I want to know those polynomials such that if there exists some number that can set it equal to 0. Okay, so let's do a simple example. Okay, here's a nice polynomial, x squared minus 5x minus 6. That's a nice polynomial. It has one variable. Okay, if you set x equal to 6, let's do this. 6 times 6 is 36. Minus 30 minus 6, that's equal to 0. So we accept. Okay, because that's a typical input that can do this. Okay, how about this? X squared plus 1, okay? I want to know when this is equal to 0, okay? Anyways, I have no idea, but if you set x is equal to square root of minus 1, you'll see that's the only time it has it. We're dealing only with integers. Okay, that's the only time that's what's called the root of the polynomial. The polynomial where that's what makes it into 0, so this is reject. Okay, he's going to reject. But how about if I do something like this? X to the 5 minus 6x to the 4 plus 13x squared plus 21x minus 52. Okay. Question, is that polynomial in this language? Yes or no? Okay, and the answer is, I have no idea. I'm going to try x is equal to 0. By the way, let's do this as a positive integer. I'm going to try x is equal to 0. I get minus 52. That's not good. I'm going to try x is equal to 1. I'm going to try x is equal to 2. I'm going to try x is equal to 3. I'm going to try x is equal to 4. I'm going to try x is equal to 5. If any one of them has the final answer as 0, I stop. Okay? But what happens if we go on and we don't find a 0? Well, when should you stop? I have no idea when you should stop. I could plug in 5,749 in here and it will stop. So I better keep on going. And if not, I better keep on going to 10 million, billion, trillion until I find one. Okay? If I find one that when you plug in it's equal to 0, then I stop and I reject. How could I possibly reject? Okay, I can't. And so this input can just go into an infinite loop. Try this one, try this one, try that one, try this one. Okay. Okay. I'd like to draw a picture now of these two things because we have to understand this in the context of all the other types of languages that we saw. Okay, so let's do our typical language. Alphabet, words, languages. I'm going to draw things a little bit smaller, closer to scale. Regular, context-free languages, context-sensitive languages. Okay, but now we have a new thing. Okay, the new thing is right over here. These are called Turing decidable. A Turing machine can decide it. A Turing machine can give a yes-no answer. By the way, for all of these, there's always a yes-no answer. Okay, for all these weaker machines, there's a yes-no answer. But now we have a new concept also. Turing recognizable. Okay, that goes in there. Okay, now if you want, Turing recognizable is where a computer can give a yes, a no, and a maybe answer. Think of an infinite thing as a maybe. But again, computers are not really giving a maybe answer. We humans are accepting it as a maybe. The computer's just going on, looking for a solution, looking for a number. But when you plug it into the polynomial, you get out 0. It's keeping on looking. Doesn't mean yes or no. Okay, so maybe doesn't mean, if you know it's maybe, then you know the answer is no. Okay, now, so it's very interesting. Ooh, skip something here. Okay, this is the old thing, now we're dealing with this. What we're going to do in chapter 4 is we're going to find a lot of things in here, decidable. Then we're going to find a lot of things that are in here, recognizable but not decidable, and then we're going to find a lot of things out there. So that's a little bit interesting. Okay, let's talk about machines. These are the machines that recognize these languages, or the machines that describe these languages are called finite automatons. The machines that recognize these languages are called pushdown automatons. The machines that recognize this languages are called linear bounded automatons. The machines that accept this language are Turing machines that always halt. They always stop. Here we have just Turing machines. Sometimes they halt, sometimes they don't. That's Turing recognizable. These are by Turing machines that don't necessarily always halt. Okay, great. I'd like to give you another example of something that's in here. And first I have to tell you what the Goldbach conjecture is. Goldbach conjecture. Okay, and this is something that goes back, to the 1700s. There was a mathematician in Germany named Goldbach, and he had the following thing. So let me just give you an example. Let me just do this. Okay, let's take the number 4. 4 can be written as 2 plus 2. Let's do another one. 6. 6 can be written as 3 plus 3. Let's look at 8. Okay, I want to write this as a sum of 2 primes. 8 is 5 plus 3. Okay, 10. 10 is 5 plus 5. That's a prime, that's a prime. Every one of these is a prime. 12 is 5 plus 7. Prime, prime. 14, 7 plus 7. 16, I could do 8 by 8, but that doesn't go, is 11 plus 5. Can probably do it another way also. 7 plus 9, no, that's not going to work. Okay, 18. 18 is 11 plus 7. 20 is 13 is a prime number. 13 plus 7. 22 is 11 plus 11. 24 is 21 is not a prime. 21 plus 3 is not a prime. 22, 23 is a prime. 23 plus 1 is not a prime. So we have to go down. 19 is not a prime. So 19 plus 5. 19 plus 5, that works. Okay, 26. 19 plus 7. Dot, 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 dot. Okay? Mr. Goldbach sat down and he wrote up a couple of hundred numbers, even numbers over 4. Can't get less than 4 because 1 is not a prime. So 4, and he made the following conjecture. Conjecture is as follows. It means, I don't know if it's true, but it seems to me that every even number more than 4 can be written as a sum of 2 primes. 1 prime plus another prime. Okay? He made this conjecture. Okay? Now, I ask you the following question. Is this statement true or false? Okay? Is the statement true or false? Answer, I have no idea. Neither does any other mathematician around. This question's been around for about 250 years, and nobody has a proof of this way or that way. However, people run computer programs, and they run to the billions and trillions, and they see that so far, every single one of them is true. Okay? So now I ask the following question. Consider the following thing. N, such that, here's a language, N is an even number that is a I don't want to write it like that. Never mind. Okay. I don't want to do what I just want to say is as follows. Question. Is there a counterexample for the Goldbach conjecture? Answer, I have no idea. Okay? I could set a computer to try to look for a counterexample. I don't know if the computer will stop. So I don't know. So with computers and math, sometimes you can get a problem where you don't have a yes-no answer. You have a yes, no, and maybe answer. Such things are Turing recognizable and not Turing decidable. Okay. We're going to see later on. Okay, we'll do that first. Okay, great. So we have these two different classes of language, Turing decidable and Turing recognizable. Okay, and it's very, very nice. Okay, great. Now, I'd like to go back to talking about the machines. This is now talking about languages. I'd like to talk back about machines. Remember we talked about regular languages, and we said we have finite automatons. Well, then we souped them up, and we talked about other types of finite automatons. We had non-deterministic finite automatons and non-deterministic finite automatons with epsilon moves. Okay? Well, we want to do the same thing, but with Turing machines. We want to soup them up. We want to get fancy Turing machines, and we see, can we get more information from that? Okay? So that's what we're going to do in the next section. So let me just tell you what the next section is all about. Well, actually, let's just start it. Okay, section 3.2, which is called variations of Turing machines. Okay? It's all about getting fancier Turing machines, okay, and seeing whether those fancier Turing machines do more or not. Okay, so there's a lot of different variations, and we're going to talk about them. But you're also reading the book on your own. So one nice variation is called a multi-tape Turing machine. Okay. And the idea is as follows. Why just have one tape which has your input, your memory, your workspace, and your output all on one single tape? Maybe we should have many tapes. So this is a typical Turing machine. It has a tape like that. Okay, that's your basic Turing machine. We've been talking about this all along. But how about having another eye and another eye, each one looking at a different part of a different tape? So you might have, if you want, you could split these tapes into different things. You can have one tape to deal with the input, one tape to deal with your memory while you're working it out, one tape to have your output. You can have K different tapes. Okay? And obviously this thing will be much more advanced. Okay? You'll be able to do things with this Turing machine that, well, I don't want to say it's much more advanced, but I just want to say it has a feel of being better. Okay? And I want to say we do this with our computers. We have a place in memory where we store our programs. We have a place in memory where we store our operating system. We have our place in memory where we store our games. We like that place. We have a place in memory where we store our where we store our movies that we download illegally. Okay? So all that is very nice. Okay? Let me just show you what a transition function would look like. So let's remember what the transition function for a regular Turing machine is. Tell me what state you're in. Tell me what you're looking at on the tape. I'll tell you what state to go into. I'll tell you what to write on the tape. And I'll tell you, should you go to the left or should you go to the right? That was a regular Turing machine. Now, I don't have one tape I have to worry about. I have K tapes that I have to worry about. Okay? That's the product of all those things. So whatever's on the tape, I need K copies of it. I also have K copies of what I can change those things on. And also for every one of my arms of my Turing machine, I can move this way and I can move that way. And so we have K over here. Okay. So let me just give you a typical thing like this. It says like this. If I'm in state Q52 and I see on the first tape the letter A, and I see on the second tape the letter X, and I see on the third tape the letter T, and I see on the fourth tape the letter S, and I see on the fifth tape the letter 1, and I see on the sixth tape the letter H with a dot on top. Okay, let's just say, let's say I have 1, 2, 3, 4, 5, 6 tapes. Okay, we'll make the dot a little bit more prominent. Then, what I want you to do is go into state 61. I want you to leave the A alone. I want you to change the X to a Y. I want you to change the T to a T prime. I want you to leave the S alone. I want you to change the 1 to a 2. And I want you to change the H to X. Okay? Then, hold on, I'm not finished. In the first tape, I want you to move to the left. In the second tape, I want you to move to the left. In the third tape, I want you to move to the left. In the fourth tape, I want you to move to the right. In the fifth tape, I want you to move to the left. And in the sixth tape, I want you to move to the right. That's a typical rule that you would have for a 6-tape Turing machine. Okay? Obviously, like parallel processing, it's much more complicated to program. but you can do things quicker. You don't have to go count here and go count there and do stuff like that. Okay, great. Now, the typical thing to say is that a multi-tape Turing machine can do things that a single tape Turing machine cannot do. Let me restate that. A typical statement is that a multi-tape Turing machine can do more things that a single tape machine cannot do. But that is not true. Okay? That is not true. And we're going to sing this song a lot today. Whatever a multi-tape Turing machine can do, a single tape Turing machine can also do. Okay? And let me just show you why this is so. Okay? So let's say you have a multi-tape Turing machine. I'm not going to draw the arms in because it makes things a little bit more complicated. Okay? And let's say this has A, B, X, 3, 6, 2, 5, blank, 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 blank. And this has, I don't want to use blank. 1, 2, 8, 3, 6, 9, T, 7, 1, and blank, 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 blank. And this has 7, 7, 2, Y, Z, T, R, 6, capital S. Blank, 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 blank. Okay, so this is a multi-tape Turing machine, and I'd like to show you how a single tape Turing machine can do what a multi-tape Turing machine can do also. Now, let me just give you intuition. Ready? There was somebody in the department that had a computer that had 14 different processors. Okay? And whenever this professor would talk to me, he would always say over, oh, this computer can do 14 processes. And I always said the following thing, and this goes back for years already. I said, oh yeah, whatever your computer can do, my computer can do also. And this is multitasking, multi-threading, etc., all those concepts. The idea is as follows. My single processor can do what that professor's 14 processors can do. It does it slowly. It does each processor individually, 1, 2, 3, etc., etc. But it does it. Okay? Same thing here. This multi-tape Turing machine can all be mimicked by a single tape Turing machine. Okay? But we have to be very careful about it. Okay? And so this single tape Turing machine will have the following. A, B, X, 3, 6, 2, 5. Then it's going to have a number sign. The number sign is going to be something, well, or some type of sign to separate what's on the tapes. In other words, this is on the first tape. Then 1, 2, 8, 3, 6, 9, T, 7, 1, a number sign. Then 7, 7, 2, Y, Z, T, R, 6, S, stop. Okay? Now, let's say there's a rule that says as follows. If you see a 6 over here, if you see a T over here, if you see a 2 on the third thing, then change. Let's see what's a typical thing that would happen is it would say change the 6 to a 7 and move to the right. Change the T to an L and move to the left. Change the 2 to 9 and move to the right. Okay, so that's a typical thing here. So this single tape Turing machine can deal with that also. What we're going to do is we're going to add new symbols which describe where the Turing machine is looking at. So we're going to put a dot over there. Okay, here it was looking at the T, so we're going to put a dot on top of that. And we're going to look at, here it was looking at the 2, so we're going to put a dot on top of the 2. Okay, and now what's going to go on is as follows. The Turing machine is going to go here. Again, the book is a little bit more exact and formal, but we're doing it essentially the same. And the book says as follows. Start here. Find what you're looking for. Find the dot. Okay, say, okay, I have a 6 on my first dot. Go here. Cross to the next barrier. Again, look for a symbol that has a dot on it. Got it. Okay, so I have a 6 on the first symbol, a T on my second symbol. Cross to the next barrier, find 2. Now, this Turing machine has the rules for this Turing machine built in. Okay? In other words, I am having this machine mimic that machine. This machine better know what's going on. I'm sorry, this machine better know what the rules are. So look in the rules. What happens if I'm in state Q53 and I see a 6 and a T and a 2? Okay? This machine will know that rule. Okay? And here's what to do. Okay? And this machine is going to go back to the beginning to change the 6 to a 7. Okay? And then it's going to erase this dot and put the dot over here. Then it's going to go here. It's going to change the T to an L. It's going to erase this dot and put the dot over there. Then it's going to change this, erase this 2, change it to a 9, okay, and move the dot this way. Okay. Then it's going to go back to the beginning. It's going to go back to the beginning and try it again. Again, look for the dots, etc., etc. Back and forth, back and forth, and back and forth. But something bad can happen. What bad thing can happen? Okay? The bad thing could happen is, let's say I'm over here, okay, and I see a 5. Okay? So let's change the 5 to a 7, fine, and then move over here. Okay? Change the 5 to a 7, and then move over here. 1 second. It can't move over there. Why? Because it has that barrier. Okay? So what I have to do is I have to move this over to do that. Now how the hell am I going to move this over? This is a tape. It has symbols on the tape. And the answer is I have to go all the way to the end, move this here, move this here, move this here, move all of this over, move this here, put in a blank, because that's what it's pointing to. Okay? So this is, like in a regular computer, this is bad memory management. Okay? When you have to spend a lot of time worrying about where things are. But again, if you're trying to do multiprocessors, there's a lot of things that you have to worry about like that. You have to worry about where the thing is. But that is fine. It's doable. It will take more time to do it this way than this way. Just think, for one move here, you have to move everything here, move back and forth for all 3 of them. You have to do it at least twice, once, twice. So you have to, for one single move here, you have to do a lot here. Okay? But again, even more than that, sometimes you have to go again and move everything slowly, move everything over so that you can make room here. Okay? And that's a lot of big pain in the neck. We will talk about this next, in chapter 7, we will talk about how much room exactly it takes. But the main point we're interested in is whatever a multi-tape Turing machine can do, can be done by a single tape Turing machine. Whatever a multi-tape Turing machine can do, a single tape Turing machine can do. This is like what we saw with the, whatever a non-deterministic pushdown finite automaton can do, a deterministic one can do. Similarly, whatever a multi-tape Turing machine can do, a single tape Turing machine can do. Great. See what other variations we can think. Okay. Okay, I just want to write that as a theorem. What I just said, I want to write it as a theorem. Theorem. A language is Turing recognizable if and only if some multi-tape Turing machine recognizes it. Okay? Now, this if and only if is this and this. I have to do it this way and this way. Let's go through this. If a language is Turing recognizable, we made this definition for a single tape Turing machine. Well, a single tape Turing machine, some multi-tape Turing machine recognizes it. Okay? And the way to think of this is the simple way. The way to think of it is, think of a multi-tape Turing machine, but just ignore what's going on in the bottom k-1 tapes. Ignore all but one tape. Don't look at it, don't program it, just forget about it. And just whatever you can do on a multi-tape Turing, whatever can be done in a single tape Turing machine, do that, but ignore the others. It's like having 14 processors, but not dealing with 13 of those processors, just dealing with one processor. Well, my computer is exactly that. Okay? Going the other way is, if I have some multi-tape Turing machine that recognizes some language, then mimic the multi-tape Turing machine with a single tape. Okay? Great. Okay, let me just talk about some, okay, so this is true. So Turing recognizable, I don't care what definition you use for Turing machine. Multi-tape or single tape, that's what a Turing recognizable language is. Great. I'm going to go through some quick other definitions, okay, and then we'll talk about an important one. One the book doesn't talk about, but every other book talks about. Usually we think of our tape as like this. Okay, it's a one-way infinite tape. It goes on forever, and you write your input over here. Some Turing machines like to think of the tape like this. It goes on this way. This is a one-way infinite. This goes on two ways infinite. Okay? Okay, now you might say, hey, this is more powerful than this. Okay? Whatever the... it's more powerful to have this. Okay? And the answer is, yes, it seems that way, but it's not really that way. Okay? Okay? Because whatever can be done here can also be done here. Okay? And I'd like to show you how. So whatever can be done in a two-way infinite machine can also be done with a one-way infinite machine. And the way we do this is as follows. We chop this in half. Okay? And we bend this over here and bring it around like this. And so you might have A, B, C, D, and you might have X, Y, Z, T. Okay? Now it's going to be, if I bring this around, A, B, C, D, and here I have an X, Y, Z, T. Okay? Now, I can have this machine mimic this machine. Okay? And the idea is as follows. It's pointing here, so have it point here. Ignore the Z and go here. Okay? Then, sometimes I move here, sometimes I move here. And if this machine would go from here to here, so then I stay here, but I look at this X rather than this. So what this is called is not a multi-tape, this is called a multi-track Turing machine. It has more than one track. One eye, not multi-tape has many eyes, one eye, but it can look at different parts of the piece of paper. Okay? So, but guess what? Whatever this can do, this can be done. I'm sorry, whatever can be done with this can be done with this, whatever can be done with this can be done with that. So that's a nice thing. Okay, here's another variation of a Turing machine. Okay, it goes as follows. Your usual Turing machine, you give it a state, you give it a letter that it's looking at, it's going to go to another state, it's going to go to another symbol that it's looking at. This is talking about a single tape Turing machine. Okay? And so far, we've seen this. Tell it to go to the left or the right. Okay? But I'd like to do something else, because a lot of times I don't want to do anything. I don't want to move the tape. I want to stay there and do the next thing with the symbol that it sees. So here's something. Little change. S. This means move the eye to the left, move the eye to the right, or just stay there. Okay? Now you might say, hey, that's a more souped up Turing machine. This can do things that a regular Turing machine cannot do. Answer, no it can't. Whatever can be done with this can be done with a regular Turing machine. And whatever can be done with a regular Turing machine can be done with this. By the way, whatever can be done with a regular Turing machine can definitely be done with this. Just don't put in rules with the S. That's a regular Turing machine. Okay? But also, you can have something as follows. You want to use a stay symbol. So here's what you do. Make a change, move to the right, then move to the left. Okay? A regular Turing machine can mimic this with two transitions. Move to the right and move to the left. Or move to the left and move to the right. Quickly, one thing after the other. Staying the same means moving to the left and then moving back. Or moving to the right and moving back. Okay? So that's an example of that. Let me give you another variation of a Turing machine. And again, all of these are exactly equivalent. Whatever one can do it, the other one can do it. Okay? Look. Think of a two-dimensional array. Okay? How does a computer store a two-dimensional array? Answer, like a one-dimensional array, but it keeps track. Same thing. Why have a simple one-dimensional tape, ticker tape, ribbon, typewriter ribbon as the tape? Maybe have the following. Have a lot of storage and have information in every single one of these boxes. And also have an eye pointing to one of the boxes. Let's say he's pointing to this box. Okay, great. But now I can store things here. Again, if the whole thing of Turing machine is adding in random access memory, then why not make my memory bigger and more dimensional than just a single tape? What a pain in the neck this is. Every time I wanted to use something, I had to go all the way here or go over there. How about having this great thing, and again, how big should this memory be? Infinite in every direction. Because I don't want to worry about how much space I have. I don't care. The Turing machine tape was infinite because I didn't care about that, and I don't want to care about this. Now, let's look at what a transition function for this would look like. You would say, tell me what state you're in, tell me what letter you're looking at. You're always looking at one letter at a time, okay? And I'll tell you what state to go into, what letter to change the letter that you were looking at to, okay? And also go either to the left, to the right, up, or down. This is many dimensions. This is 2 dimensions. By the way, you can have a 3-dimension, 4-dimension, 5-dimension, etc., etc. Now, question, is that more powerful than a regular Turing machine? No. Why? Because just like a multi-dimensional array can be mimicked by a single-dimension array, so too a multi-dimensional memory can be mimicked by a single-dimensional memory. Okay? And that's that. Okay, great. one more variation, and then we'll stop with the variations because we're getting sick of it, because so far what we've seen is that every single variation that we had turns out to be exactly the same as a classical Turing machine. So what's the purpose of all these things? And the answer is when you write programs with these multi things, they're harder to program, just like multi-processing programming and parallel programming is harder to program, but they can be done in, here's the key word, fewer steps. All these things can be done. If you have all these souped up Turing machines, then programs can be done in fewer steps. Okay, so that's why we like them. Okay, so now for the most important one, okay, and the one that's actually going to show up the most, okay, and that is, you've been waiting for this word, non-determinism. So I'd like a non-deterministic Turing machine. Okay, and so let me just show you what that would look like. The transition function would say as follows. Tell me what state you're in. Tell me what symbol you're looking at. And I'll tell you, hold on. I'll tell you not what state to go into, what symbol to write, and whether to go to the left or the right. We're talking about a classical Turing machine, but a whole bunch of them. A whole set of different things that you can do. And again, this is very similar to a non-deterministic finite automaton. You have many different possible paths that you can try, and you have to look at all those possible paths and see how they work, and see which one works and which one doesn't work. Okay, great. Now, question, is non-deterministic the same thing as deterministic? Let's go through our previous. Okay, the previous examples were as follows. We had deterministic finite automatons. They are equal to non-deterministic finite automatons. Okay, and we proved that theorem. We proved it nicely. Okay, we said whatever can be done here can also be done there. Then we talked about pushdown automatons. Okay, and we had deterministic pushdown automatons, and we had non-deterministic pushdown automatons. Okay, and if you remember correctly, we only talked about these guys. We did not talk about these guys. Okay, and the reason why we didn't talk about these guys is because they are not equivalent. They are not equivalent. Okay, and these guys are equivalent to context-free languages. These guys are not. Great. Now, we're talking about Turing machines. Okay, and so we have non-deterministic Turing machines and deterministic Turing machines. Okay, and the question is, are they equivalent or are they not? Answer, they are. They are equivalent. Whatever this guy can be done, we're going to mimic, we're going to find a deterministic Turing machine that's going to mimic it, and it will be able to be done. Okay, how it's done, I don't want to talk about that now. I will talk about it, I promise you I will talk about it in, don't move. Sorry. Well, I will talk about it in chapter 7. Okay? I will talk about it in chapter 7. Okay? But I'd just like to show you how the proof works. Okay, we're going to go deeper into it in chapter 7, but I would like to show you how it works. Okay? So let me show you the way a non-deterministic Turing machine goes. It starts off here. This is going to be your starting configuration. And there's going to be 3 possibilities, or a bunch of possibilities that it can do. Now this guy could have a bunch of possibilities that he can do. Each one of the tapes has a bunch of possibilities. then this guy can do one possibility. This guy can die. This guy can do two possibilities. This guy can do one possibility. This guy can do one possibility. This guy can do two possibilities. This can be three possibilities. This can do three possibilities. This can do four possibilities, etc., etc. Okay? So, and the same thing that we saw with finite automatons are going to be done here. If at any one of these this is an accepting state, then the word is accepted. The beginning word is accepted. And what a non-deterministic machine does is it tries all these possibilities at one time and gets that. Okay, but the point is here, this is one step, time step, two time steps, three time steps, and you get an accepting answer. Great. Now, how will a deterministic machine mimic such a machine? Okay, and again, the idea is, the intuition is parallel processing. How can a single processor mimic a multiprocessor thing? And the answer is, you try every single possibility. You do every single possibility. Okay? Okay? And so the way to do it is as follows. You have a Turing machine that's a deterministic Turing machine that starts off like this. It's then going to try this possibility, then it's going to try this possibility, then it's going to try this possibility, this possibility, this possibility. Okay? What it's going to do, and we're going to go through it more in detail in Chapter 7, is going to try each possibility. It's going to say, okay, what happens at this configuration? 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 What happens in this configuration? Is it an accepting state? Is it an accepting state? Then it's going to try this, 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 this. As soon as it comes here, it's going to see this is an accepting state. It will accept. Okay? But if not, it will go on and on and on, doing exponential amount of configurations, checking each one of them. Okay? And if it finds any accepting, it accepts, otherwise it keeps on going. If it finds rejecting, it doesn't do that. Okay. Okay. So we'll go through this a little bit more carefully when we see this in Chapter 7. Question: what can a non-deterministic machine do? Answer: whatever a what can a non-deterministic and a deterministic machine can do the same things. Okay, great. Okay, now we have to just talk about section 3.3. Okay, we're up to the last section of Chapter 3, and it just deals with a lot of little topics that are important, but nothing in order. Okay, the first thing is the idea of an algorithm, and basically what they want you to do is get the following impression. The following impression is that with these Turing machines, you can do anything that a regular computer can do. Okay? Let's go historically. Turing wanted the idea of a computation. This is 1930, before computers were around. So he invented this thing. And then he saw he can do addition, he can do multiplication, we did doubling, he could do this, he could do that. A lot of different things he can do. Just a little history. Turing was an Englishman who came to America to do his PhD. He came to Princeton to work under a guy named Church. And he had this idea of what a computation is. And he showed Church. And Church at some point said, you know what, anything that can be done as a computation can be done by your machine. Okay? And Turing started coming out with these different programs showing, I can do this, I can do multiplication, I can do exponentiation, I can do loops, I can do this, I can do that, I can do while loops, etc., etc. And so then they came out with what's called the Church Turing thesis. Okay, and the Church Turing thesis is an idea that says anything that any computer can do, a Turing machine can do. Okay, and that's a very important thing. Anything that any computer can do, a Turing machine can do, and anything a Turing machine can do, any computer can do. But more interesting is the other way around. The other way around says as follows: anything that a Turing machine cannot do, no machine can do. Okay? Anything that a Turing machine cannot do, no machine can do. Okay? So again, Turing invented a device that he thought can do what computers can do. The Church-Turing thesis says they got it right. Whatever a computer can do, a Turing machine can do. Whatever a computer cannot do, a Turing machine cannot do, and vice versa. Okay? Now, that's interesting because later on in Chapter 4, we're going to see that there are certain things that a Turing machine cannot do. Now, that's not just interesting for Turing machines, that's interesting for all computers, because if a Turing machine can't do it, no computer can do it. Okay? Just a little thing on the language. So this was an idea, it's a conjecture in some sense. It says that Church and Turing had, that Turing machines are very important for everything because what they can do and what they can't do. Okay, why is it called a thesis? Why not a theorem? Okay, because you can't prove it. Okay, you can conjecture it, but you can't prove it. Why can't you prove it? So the proof would be something like this. Whatever a computer can do, a Turing machine can do. Okay, what can a computer do? I don't know. We're in a computer department. Whatever a computer can do, a computer can do. Yeah, but exactly what functions can a computer do and what functions can a computer not do? Okay. Anyways, it's hard to describe that. We obviously have thousands and thousands of computer programs, so we know thousands of things a computer can do. Okay, and we're going to see in next chapter, chapter 4, we're going to see hundreds of things that we're going to see a few things that a computer cannot do. But how do I make that demarcation? How do I give you an exact definition of what a computer can do and what a computer cannot do? If I gave you that exact definition, I have an exact definition of a Turing machine, I would show whatever can be done here can be done here. But I don't have an exact definition of what a computer can do and cannot do. Okay, so that's why it's a thesis. I cannot give an exact definition of what a computer can do because I don't have it. So Church-Turing thesis says, look, you kind of have an intuition of what a computer can do. A Turing machine can do that. That's that. Okay, so this is an important thing. Church's computer came out almost 90 years ago. Turing's idea came out almost 90 years ago, and no one has found a counterexample to that. So that's why it's very important. I want to spend the last 2 minutes talking about encodings. Okay. Turing machines are very interesting. They deal with strings. But you know what? I don't want to deal with strings. Computers deal with numbers, they deal with polynomials, they deal with pictures, they deal with etc., etc. They deal with games, etc., etc. They deal with lots of different things. So I don't want to only deal with strings. Well, Turing machines only deal with strings, but you know what? You can encode things as strings. You can encode things as strings. So for example, okay, and by encoding things with strings, you can manipulate the strings, and by manipulating the strings, you are manipulating the things. And then we have whatever one computer can do, the other computer can do. So that's all about encodings. I just want to say, you have different types of computers that were created to do different types of things, like special graphics computers and number computers and different things. Well, all those, what they're really doing is they're instead of having things encoded you have a type of object encoded one way and decoding it and things like that. If you make the computer to be specific for one particular purpose, it can be very fast for that. So you don't have to worry about encodings. But let's just talk about encoding things. For example, here's a typical polynomial. Okay, I'd like to show you how I would encode this. Okay, think about a polynomial. It's not really important what variable you use. You could use y also. So the only thing here is really important is you might want to say 3, 5, you know what, let's make that -7, minus 7. Okay, and you might say, this is an encoding of a polynomial. Okay, and you can have different polynomials to do it. Now, I could have done this another way. Here's another way of doing it. Let's do this. Plus 111 semicolon plus 11111 semicolon minus 1111111 1, 2, 3, 4, 5, 6, 7. Okay, semicolon. That's another encoding of these things. And the point is, you can encode polynomials many different ways, and each one is legitimate for their own things. Okay, how about this? Let's say I have a polynomial that's like this: 13x squared y plus 17xy squared minus 13y to the third plus 7y minus 6x plus y. Okay? This is a polynomial in 2 variables. Very nice. Now, how should I encode that? I not only have to tell what each thing is, because I have to tell, I need 2 types of things. I got to tell what the power of x is and what the power of y is. Here, this is y to the 1. This is x to the 1 y squared. This is y to the third, x to the 0, x to the y to the 1, x to the 0. You got to do that. Okay, I have no idea how to do it. I mean, I can think of different ways of doing it, but what we're going to talk about is there is some way of encoding it. There is some way of encoding it, and we write the encoding like that. Okay? Okay. Now, here's an example of polynomials, but obviously we're going to want to encode other things too. I'd like to give you a sampling of some of the things that we're going to encode, okay, to get a feel for it. For example, here's a graph. Okay. Now, there's a lot of different ways of thinking of how to encode this. Okay. So, for one, by the way, this is a graph, but you might want to put numbers on it, on the nodes, and then you can encode this as follows. 1, 2, 3, 4. That tells me who my graph, who's the nodes, the names of the nodes in the graph. I have to give them names because I have to talk about how they're connected to each other, and I can't talk about them unless I give them names. Okay? And then I could say, comma, 1 is related to 2. 2 is related to 3. 3 is related to 4. Comma, 2 is related to 4. Okay? That's an encoding of this thing. And I can use this on the, I could put this, why do we want to encode things? Because we want to put them on a Turing machine tape and see and manipulate things. So that's our goal. Okay? There's another way I can encode this thing. I can say as follows: 1, 2, 3, 4. 1, 2, 3, 4. Okay. I say 1 is connected to 2. Okay. All the rest are 0. 2 is connected to 1, 2. I'm sorry. 2 is connected to 1, 3, and 4. 3 is connected to 2 and 4. 4 is connected to 2 and 3. Okay, that's encoding a graph as a matrix, and then I can encode a matrix as a string. That's what our ultimate goal is, as follows: 1, 0, 1, semicolon, 1, 0, 1, 1, semicolon, 0, 1, 0, 1, semicolon, 0, 1, 1, 0. So I've just encoded. So here's a graph. I can encode it as a matrix. I can encode it as ordered pairs of who the edges are. I can encode that as that. Okay, great. But I don't only want to encode. Okay, so if you want, you can call this as G, and then this is an encoding of G. This is an encoding of G. This is an encoding of G. Different ways of encoding things. But you know what? I don't only want to encode graphs. I also want to encode finite automatons. Okay, so let's do that. Let's do what's a finite automaton. Okay, so a finite automaton I don't care. Non-deterministic or deterministic, I don't care. So I might do this as follows. I might think of a graph as, I'm sorry, I might think of a finite automaton as a graph. And so watch the way I can describe a finite automaton. What's a finite automaton? It's a 5-tuple. Q, again give the alphabets, then give the transition, then give the Q0, okay? Then, you know what, I'm going to put semicolons here just to make them different. Then give the final states, okay, the accepting states. Okay, so I'd like to encode this finite automaton as a string. So I'm going to do it as follows. 1, 2, 3. Those are my 3 states. Semicolon. What strings? A, B, C. Semicolon. That's the second thing. Okay, leave me space here for the transitions. Okay, no, don't leave me space. Let's do it right now. Okay, let's do it right now. Here's the way I'm going to encode the things, and I'm sure you can think of a better way of doing it. I'm not interested in, at the moment, I'm not interested in the better way. Sometimes we might be interested. Okay, here's what I say. I'm going to give each one of the rules as a triple, as follows. Ready? If I'm in state 1, comma, and I see the letter A, comma, I go to state 2. I just described that. Comma. If I'm in state 2, and I see the letter A, then I stay in state 2. Comma. If I'm in state 2, and I see the letter B, then I go to state 3. Comma. If I'm in state 3, and I see the letter B, I stay in state 3. Comma. Now the last one. If I'm in state 3, I see the letter C, I go to state 1, semicolon. Okay? That's all the rules. Now let me tell you what the starting state is. 1, that's the starting state. And finally, what's the accepting states? 2 and 3. 2, 3. This whole thing, this whole sequence, can be an encoding of a finite automaton. So this is M, okay? Then the encoding of it will write like this. Okay? Now, I just made up this encoding. I'm sure you can think of a better way of doing it. You might just write, look, here's another way of doing it. 3, that's giving the number of things. Then, okay, maybe you want to use commas. Maybe you want to use arrow like that. A, B, C. And then you want to do the transitions. So you might do something like this. 1A2, comma, 2A2, comma, da, 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 da. Then you want to do semicolon, or not, arrow 1, comma, 2, comma, 3. I don't know. There's lots of different ways of encoding. The main thing is as follows. If the computer knows how it's encoded, or the Turing machine knows how it's encoded, it can figure out what the thing is. And it can decode it. It can manipulate the object. That's the whole point. Okay, great. Not only are we interested in finite automatons, but we're also interested in encoding not only finite automatons, but we're also interested in encoding Turing machines. Turing machines are very interesting. So for example, I can write this. A, change it into an X, move to the right. And here, this is B, change it into a Y, move to the left. And here's this, and we can write this is X, change it into a T, move to the right. And this is B, change it into a B, move to the left. And this we can write as C. You see a C, change it into a C, and move to the right, something like that. Okay, now a Turing machine I can also encode. And you can encode a Turing machine by, let's say, giving the states, 1, 2, 3, semicolon, giving the alphabet. Okay, but here we're doing the tape alphabet. Okay, so you might write A, B, C, X, Y, T. That's the tape alphabet. Great. Then you want to say the rules. So the rules are now as follows. Now the rules are 5 tuples. It says, if I'm in state 1, I see the letter A, I want you to change it to an X, move to the right, go to the state 2. Okay? And you can have a lot of 5 tuples like that. I don't want to do that, whatever. And then you can ask, what's the queue accepting, what's the queue rejecting, what's the queue starting, etc., etc. Okay, so if this is a Turing machine, M, then this will be the encoding of the Turing machine. Okay, but why are we interested in this? Very simple. We want to have Turing machines talk about Turing machines. So we want to be able to encode Turing machines so that we can have Turing machines talk about Turing machines manipulating Turing machines deciding properties of Turing machines. That's what we're dealing with. Okay? And that's what this section is all about. It's about encodings, but we don't get into technical because you can think of a way of encoding things, I can think of a way of encoding things. They're all very simple to imagine. Okay? Okay, great. I think that's enough for Chapter 3. We are now finished Chapter 3. Have a great day.